Welcome to this lecture. Before proceeding forward, let us first quickly recall what we have done in this week. In this week, we have concentrated on looking at structural properties of measures. In particular, we have seen these two very important results called the Lebesgue decomposition theorem and the Radon-Nikodym theorem. Using these results, we have obtained important decomposition results for general probability measures on the real line together with the Borel sigma field. Using that decomposition, we have also talked about the corresponding decompositions about the distribution functions, right? And using these decompositions, we have talked about the corresponding classes of random variables or random vectors. In particular, we have concentrated our attention to these absolutely continuous random variables which correspond to the random variables with law being absolutely continuous with respect to the underlying Lebesgue measure. With these absolutely continuous random variables at hand, we are now moving on to their properties and analysis involving these random variables. We are going to look at expectations for these random variables. Let us now move on to the slides for this lecture. So in this lecture, we are going to discuss about the computation of expectation for these absolutely continuous random variables that we have discussed. Alright. But then we will also comment about the higher dimensional versions of this. So we will also consider absolutely continuous random vectors. We are going to see some inequalities involving the moments after we discuss these expectations. Okay, so we have earlier discussed about expectation for general random variables, then for the special case of discrete random variables. Now we finish the discussion about expectations for absolutely continuous random variables, and putting everything together, we are going to look at certain inequalities that are applicable to all these situations. Alright, so let us first start with the notations. So given some absolutely continuous random variable, call it x, defined on some probability space omega fp, and a Borel measurable function g, which is taking values on the real line and defined on the real line. So if you take these things x and small g, then remember g composition with x, so that is g of x, so that is a random variable again defined on the probability space. However, this is not necessarily absolutely continuous. For an example, take g to be a constant function. Okay, so then g of x is just a constant random variable. You can treat it as a degenerate random variable, and this is not absolutely continuous. So therefore, you have to be careful with this choice of g. Now you may have seen these kind of results, certain sufficient conditions on the function g, which will allow you to claim that g of x is also absolutely continuous. These sufficient conditions are usually in terms of regularity of this function g. Alright, so let's recall this result. However, please note that we are going to state this without proof, assuming that you have already seen this result in your basic probability theory courses. And also, we are not going to state this version in higher dimensional case. Again, this result can be generalized to the higher dimensions. Alright, so let us see this result. So we continue with this setup that we have an absolutely continuous random variable x and we have a nice measurable function. So let us now look at what are these conditions we impose on this function g. So suppose you take g to be differentiable. In particular, notice that g must be continuous and hence it is Borel measurable. So this is a special type of a measurable function. Now, in addition, you also assume that g prime is strictly positive for all points. That will ensure that your function g is 1 to 1 and strictly increasing. In this case, what you claim is that the random variable y, which is given as g of x, is also an absolutely continuous random variable, and you can in fact write down its PDF given by some such formula. Now remember, if the function g is strictly increasing and 1 to 1, you can consider the inverse function, and that's the inverse function that appears in this formula. Alright, And then here, just to note, there are certain range of values for this random variable capital Y, which is given as this range of values. So this is g of minus infinity to g of infinity. So what are these values? These values are nothing but the limit of the function g as x goes to infinity and limit of the function g as x goes to minus infinity. Alright, and here f subscript x denotes the usual notation, that's the PDF of the given random variable capital X. Alright, so with respect to all of these terms, you can write down the PDF of this random variable y, which is g of x. Now there are these other sufficient conditions. For example, you can take g prime x to be negative for all x, and you will get a similar result for this. Alright, and for a higher dimensional case, the result usually involves this Jacobians of these functions g. Alright, so let's not go into that details, but this is a standard result that you may have seen in your basic probability courses, and we are going to assume this. This is just for the record that we can figure out certain sufficient conditions under which g of x becomes absolutely continuous. Alright, but now our main interest is in the computation of expectation for absolutely continuous random variables or random vectors. So here we are doing the setup in higher dimensional at one go. Alright, so suppose you start off with a random vector x taking values in Rd. So here d could be anything 1, 2, 3, 4, any such dimensions. Alright, so suppose you write the PDF as a subscript x. Then what is the definition? So by definition, the Radon-Nikodym derivative of the law of the random variable, which is p compose x inverse, that has this density function with respect to the Lebesgue measure in this dimension, right? So that's the idea, that you take the Lebesgue measure on Rd and look at this Radon-Nikodym derivative of the law. That will give you the density function, and that is your probability density function. So this result we have already seen. But we have also identified that we can transfer integrations with respect to p compose x inverse into an integration involving the Lebesgue measure just by multiplying by this function. So this was mentioned in exercise 4 part 1. Okay. So then what do? You apply this exercise and observe this set of equalities. So expected value of x, the random vector x, as defined, it's the value of the random vector integrated against the probability measure. Alright, and here if you do the change of variable, you will end up with this structure, that it's the integration over Rd. So here small x is in Rd. So we will make a clarification about this d-dimensional integration in a minute. But formally, let's accept this equality is true. So this is just a change of variable formula or change of measure formula that we have been using so far. But now if you change measures from p compose x inverse to the Lebesgue measure by using that Radon-Nikodym derivative, you can bring in the density function here. So that's what we have done. That's what this exercise suggested. And then what you do is that you observe that this is the usual integration with respect to the Lebesgue measure, and using the standard notational terminology that we have introduced, this is just for notational convenience, that we will simply write it as usual dx. Okay, so that's what it is. Now these equalities will hold provided one of the integrations exist. But now we have to clarify this issue about integration in Rd. So here this small x or x omega, all of these are taking values in Rd, and we have only explained about integration of extended real valued functions or real valued functions. So here these terms small x and expected x, such terms are now Rd valued. Okay, so let's make a clarification about this. So what do we mean by these equalities is that the equality is interpreted component wise. What do I mean? So you take ith component of capital X, that's what you put it in. So this will be x superscript I, let's say, that denotes the ith component of capital X. And if you do the change of variables appropriately, you will go to here. Okay, so that is the idea. So this equality holds component wise. So that is the idea. But again, you can also do this change of variable in the Rd dimensional setup. So that will give you this formula. So again, if you define the integration of Rd valued functions exactly in the way we have defined the real valued integrations, then we will get the similar results. Okay. So again, one way is to define it component wise. Another way is to define the integration directly in RD and do this in change of variable formula in this d-dimensional setup. Either way works. Okay, so that is this meaning of these equalities, provided one of these integrations exist. Now what do you do after you interpret this? You can do a usual analysis involving your expectation and do computations. Okay, so continue with these notations that x is a absolutely continuous random variable and g is a Bodel measurable function defined on R. Okay, and take y to be g of x. Then what you can try to show, this is a usual result that we have discussed earlier for general random variables and also for discrete random variables, and this is again true for absolutely continuous random variables, that the expected value of y is given as this expression provided the integrations exist. But then this y is nothing but the expected value of g of x, because y is g of x itself, and then g of x you can compute in terms of the law of capital X. So this is the integration that appears here. So you have gone from integrations with respect to the law of capital Y to the integrations involving the law of capital X. So that is the meaning of this equality. So provided one of the integrations is defined, if it exists, you can make sense of these equalities. Alright. But then look at this last expression. So here the law of capital X appears, and then if you know that capital X for you is absolutely continuous, just put in the probability density function there. So you will get this expression, the familiar expression for the expectation of g of x, where you are multiplying the function g by the probability density function and then taking the integration. Alright. So again, in all of this we have to first ensure that the integrations exist. But it is important to note that in these computations now we are not assuming any structural properties of the function g other than that it is Bodel measurable. So this is valid for any Bodel measurable function. Okay. So in this case, remember the random variable y, which is g of x, need not be absolutely continuous. Even then you get these expressions for accepted value of y, which you can compute in terms of the probability density function of x or the law of x. Okay, so this is the power of measure theory. Alright, great. And then by choosing appropriate functions g, you can talk about the moments for this absolutely continuous random variables x. Okay, so these are these moments of the random variable x about the point c. Alright. Now what do you observe so far is that these above expressions for the expectations is matching with whatever you have seen in your basic probability theory. So what we have done in an earlier week, when you have been discussing about these discrete random variables, we have got the usual expression for the expectation of discrete random variables. Now we are talking about absolutely continuous random variables. Again we have got the familiar expression, but all of these can be derived from the general theory of measure theoretic integration. So that is the power of measure theory, that all of these special cases for discrete random variables or absolutely continuous random variables are appearing as special cases, but the general theory is allowing you to do all of these computations in pretty general setup. Alright. So now you can redo these exercises from your basic probability theory, that for standard random variables you can try to compute the moments. So this is left as an exercise. But then what you have done in your basic probability theory is that you have also looked at all of these properties involving variances, covariances and other things, and you can now repeat these same arguments as soon as you have achieved the same quantities. Okay, so you have gone to these same moments, but you have now been able to define them in a more concrete fashion than what you have seen in your basic probability theory. But now you can repeat all these usual analysis as you have seen in your basic probability theory. So you are not repeating that part, but you can already fit it together with this measure theoretic arguments. Now for this normal random variables, we had mentioned these parameters mu and sigma squared. So you can now identify it with the standard identification that mu becomes expected value of x and the sigma square is the variance of x, which is nothing but this second moment of x about this mean. Alright. So now recall this discussion from note 26 of week 7. So there we had mentioned some things about characteristic functions. So in particular, we had mentioned these characteristic functions for general random variables, and then in specifically we have mentioned that we can do these computations for discrete random variables. But then for absolutely continuous random variables, from our earlier understanding once more, you can now go and obtain some nice expressions for the characteristic functions. So again, if you have a absolutely continuous random variable capital X, look at this characteristic function, which is this expectation of exponential I u x. So here u is a real number, so u varies and it's giving you this function. Alright, but now if you split this real part and the imaginary part, you get these cosines and sines, and that you integrate against the p compose x inverse. So that is the usual definition for any random variable capital X. But now if you know that your random variable capital X is absolutely continuous, you put in the density function, right? And if you put in the density function and club these integrations together, you get back this familiar expression that you have to integrate exponential I u x multiplied by the density function. Okay, so again what we are using here is that you are changing the usual integration in terms of the law of x to the integration involving the Lebesgue measure, and we have used the standard notational terminology that we have introduced in this course. So we are not writing down this Lebesgue measure explicitly, but it is understood that this is interpreted as a Lebesgue integration. Of course, if you can do the integration in the Riemann sense, then you can get the same value. Okay, so maybe the Riemann integrations will be easier to compute. So then you do that and take it as the value for the Lebesgue integration. Alright, but here it is the powerful use of this Ladon-Nikodym theorem that is allowing you to go from this law of capital X to the integration involving Lebesgue measure. Alright, now this is for the one dimensional setup, that when x capital X is a real valued random variable. But now what happens if you consider any RD valued random vector? So here again you can go via the standard definitions that you may have seen in your basic probability theory. So but now what you have to do is to interpret all the things accordingly in the measure theoretic setup. So here for any u in RD, what do? You look at this function phi x evaluated at the point u. The value is given as the exponential I u dot x. So u dot x is the usual dot product, which is given as this I times the sum of these component wise products, right? So if uj's are the components of u, xj's are the components of capital X, then you look at this component wise products and add them up, and this complex number I is just in front acting as a scalar. But now as per our understanding, this integration is nothing but the integration with respect to the underlying probability measure, and if you change variables, you just go from this integration to an integration involving the law. Okay, so this is an integration with respect to the law of capital X. But now again you can go back to the usual ideas that you can replace this law for an absolutely continuous random variable and just bring in the density function and write it as a Lebesgue integration. Okay, so that is the idea. Great. So this here again you can do this usual computation for characteristic functions in d-dimensional setup. Okay, for discrete random variables, what do? You write this p compose x inverse as this convex linear combinations of Dirac masses, and that's it. You do the usual analysis and get this finite sum or a countable sum accordingly. But now we again recall an important comment as mentioned in note 26 of week 7, that this characteristic function uniquely determines the law of this random vector x. So in week 7 we had mentioned this fact when we were talking about one dimensional case, but now we are saying that this is just the generalization to higher dimensions, and here again if you know the characteristic function, then the law of capital X, which is a random vector now, is also uniquely determined. Alright, so let's move forward. So now you can recall from note 25 of week 3 that you can identify the components of random vectors as random variables, right? So let's put in the notational terminology as appropriately. So suppose capital X is a random vector with these components x1 up to xd. Then what we have said at that time is that this is a random vector defined on this probability space if and only if the components are also random variables on the same probability space. Alright. So and then what we have said is that if you are given this one dimensional random variables, you can put them together and obtain the random vector. So this was the identification through this coordinate wise projection maps and compositions of the random vector x. So this was the idea that was used to prove this connection. Alright. Now more generally, what you can now do is that you can choose n such coordinates, call them j1, j2, jn. So we are putting it in the increasing order, so these are all distinct. Now what do? You choose these values j1, j2, jn within 1 to d. Okay, all right. And then what you can do is that you can look at this continuous map which is from rd to rn, which maps any vector small x1 up to small xd to n vector with these components. So you ignored all the other components of the original vector x and just write down the components corresponding to this j1, j2, jn. Okay, so just write them down. So that will give you this map from rd to rn. But observe that this is a nice continuous map and hence this must be Borel measurable. So therefore, as a composition with the random vector x, it will now give you this random vector which is now n dimensional. So from the d dimensional random vector, by this appropriate projection maps, you have now obtained a Rn valued random vector. Okay. So now if you continue with these notations that we have just discussed, you can show is that this random vector, n dimensional random vector, must be discrete provided the original random vector was discrete. Okay. So if you start with a discrete random vector, apply appropriate functions on this, you will get a discrete random vector once more. Okay. So that is the idea that is being used here. But here is a question. Can you make a similar statement for absolutely continuous random vectors? So if you take x to be a absolutely continuous random vectors, can you make a similar statement? Try to check this. Now we continue with the same notation. So we are still interested in this random vectors and this individual collection of components which again give you some lower dimensional random vectors. So as mentioned above, you can compute this law or distributions of these n dimensional random vectors from the given random vector capital X. You can do that. Alright. So this is just an appropriate change of variable formula. So you apply that function g and by these appropriate transformations you can obtain this law for this n dimensional random vector. But these n dimensional distributions that you obtain are usually referred to as the n dimensional marginal distributions of the original d dimensional random vector x. Okay. So again, just to repeat, we are saying that you choose this n many components out of the original d many components and look at the law or distribution of these component random vectors. So this is the joint distribution of these n many random vectors. Now you can obtain this law or distributions, and for each such combination of n many components you get one such law or distribution. Alright. These collections of n dimensional distributions we shall refer to as the n dimensional marginal distributions of capital X. Now it's important to note that given this capital X, you can immediately obtain the marginal distributions. However, the converse is not true. Okay. So if you are given all these marginal distributions and you are asked to figure out the law of capital X, it's not uniquely determined. Alright, so this converse is not true. So what do? You should try to find an example which shows this, that given this marginal distributions, you can possibly get two different random vectors with different laws such that the marginal distributions remain the same but the laws are different. So that is the idea. Okay. So please try to figure out such an example. Now, with this analysis, we have managed to wrap up all the ideas that you have seen in your basic probability theory and have connected the computations of discrete random variables and computations for absolutely continuous random variables in terms of the expectations and moments to the usual formulas. Okay, so we have used these measure theoretic structures, but we have obtained these formulas that you have seen in your basic probability theory. Good. Now we also have seen this connection with Riemann integrations and Lebesgue integrations. So that also came up as a special case of this measure theoretic integration. With this, we can understand the power of measure theory that can cover all of these distinct situations under the same umbrella. Okay, and therefore you can apply all these general results that you may have obtained in your measure theoretic setup, and individually they will give you results in these special cases. So we are going to see much more analysis about these moments and variances and covariances of these random variables and vectors in the next lecture. So this is what we are going to discuss in the next lecture. We stop here.